Hello everyone, welcome back to my channel or welcome to my channel if this is your first time watching one of my videos. I make videos on basic chemical engineering concepts and in this particular video I am going to show you how to perform interpolation and why it is necessary for chemical engineers like us. Now, if you have taken engineering mathematics course, you'll be knowing that interpolation is a very valuable technique which is generally used to estimate values if a given set of data points is available. Now, how is it important to chemical engineers? So basically, if you are running a very complex simulation, sometimes you will have some continuous property functions, and maybe those continuous property functions are not explicitly available to you, so you have corresponding data sets. Like in this particular example, I have taken up an experimental data where the temperature and its corresponding density data is available with us. Now the power of interpolation is such that uh, if I want to estimate the density value at a particular temperature point which lies within the data set but is not given to you explicitly, then I can use the interpolation function. Now, here we are going to do exactly that. This is a property estimation exercise, and we have 5 temperature points, and correspondingly we have 5 density data points which are given as rho. Now, before we start interpolating and finding out what the value of density is at the target temperature, which is given to us as 295 Kelvin, we need to call some suitable library functions. And for that, I'm going to call the scipy library. So from scipy library, I call the interpolate function and import interp1b. So this will be used for the interpolation. Now, I already have the temperature data and density data available. So the first step that I'm going to do is we are going to create an interpolation function. Okay, what is this interpolation function? Basically, it gives you an approximate continuous function to represent the data. Okay, so let me write the interpolation function. Let me call it interpolation function itself. And how are we going to do it? So we are going to use this interp1b function, and the first argument that goes here is the temperature data, because it is basically the independent data, the x data that we are going to use. The next argument that goes in is the density data, which is the dependent data or the y data. Okay, now I can use three kinds of interpolants over here, namely linear, cubic, or quadratic. Okay, so if you want to know more in details about it, you can look it up. You can look it up on uh, general resources for Python. You have similar functions available in your MATLAB as well as in GNU Octave. Now, for simplicity, I'm going to use the linear interpolant. Okay, so this particular statement is going to give a give an approximation of the data points that we are using over here. Now the next step is the actual estimation step. So now we are going to estimate the density at the given query point. So for that, I am simply going to write, let me call it estimated row, the variable where I'm going to store my result. So I'm just going to call this interpolation function that I have just created with the query point, that is target t. Okay. Now, of course, once you run this, the variable will be stored in, estimated row will store the actual result. If you are just writing this as a snippet in a very large code, then this is what you have to do. But since this is a small snippet of the actual code, I'm just going to print this result in a formal way. So for that, I'm going to write like the estimated density at the temperature target T in Kelvin is equal to the variable estimated rho in kg per meter cube, right? So this should display the result to me in a formal way. Now let me run this code. Okay, here I get an error message, so I have missed out a comma over here. Now giving a final check to my code, I'm going to run this. So once I run this, the result is displayed in the console. So I get that the estimated density at 295.0 Kelvin is equal to 978.15 kg per meter cube. So, like I said, this is a very, very simple example, and it is meant to be used as part of larger, more complex simulations where you are designing some process or doing some analysis or optimization studies. But demonstrating it on a simple example, I hope this has piqued your interest, and maybe you can actually change the kind of interpolant over here and explore how the value changes, whether it changes at all. For large data sets where you need to correctly estimate the nature of the property function, different kind of interpolants come to use. That is it for today. Thank you. See you again.